going to tackle about the epicenter problem, which is the epicenter problem is a well-known facility location issue putting P-similar facilities on a network in order to minimize the maximum distance between demand nodes and their closest facilities. Also, it is another subset of covering class of discrete location problems. As in the other covering problem, we have a set of demand nodes I which cover by a set of facility location J. Demand node is covered by a facility if the distance between the demand nodes and the facility is less than the coverage distance for the P center problem. We have P facilities when we are trying to locate them to minimize the maximum coverage distance needed to cover all the demand nodes. So this slide shows the input and decision variables needed to formulate a linear program for the P-center problem. So as you can see, we have D sub ij, which is the distance between demand nodes I and candidate site J, and P, the number of facilities to locate, and we also have two decision variables, which is x sub j represents if we locate a facility at location J, and y sub ij represents if demand nodes I is assigned to J. We also have W is defined as the maximum coverage distance. So this slide shows the formulation of the P under the problem. This slide shows the formulation of P under problem. The objective is to minimize the maximum coverage distance, and we have these constraints, and for the first constraints ensures that all demand nodes are covered. So you can see there that all elements of I is an element of I. So the second constraint limits the amount of facilities we can locate. The third constraint ensures that a demand node can only be covered by a location if a facility is located at the location. The fourth constraint forces W to equal the maximum distance, and the final two constraints are for integrality and non-negativity. Let's go for an example problem. As you can see there, there's a shape there, and there is letters that represents the location, and numbers which represents the coverage distance. You can see this shows an example network and solution for the P-center problem. This network consists of 6 locations each, with an identical demand facilities may also be located at any of the positions shown on the table. The table shows where the facility should be located based on P and the maximum coverage distance associated with P facilities. To put this in context, real-world example of these. For example, the real problem for this example is that imagine there's a car dealership at locations A through F. The owner of the dealership needs to locate. It needs to choose the location or location to serve as training facilities for all the other location, and he wants to minimize the maximum distance that his employees have to travel to train. So in this example, if he locates one training facilities there, employees will have to travel a maximum distance of 15. We can see that in the table, first part of the table. If he locates 2 facilities, so they will have to travel a maximum distance of 10, and etc., as you can see in the table. Next example, is the stochastic weighted minimax transfer point location problem. So we have to consider the following additional notation. W sub I is equal to weight associated with demand point I, which is I is equal to 1. P sub I U is UIVI coordinates of demand point I. So let's assume that the location of the facility is X sub 0 and Y sub 0 is known, and each demand of I has coordinates of P sub I, UI, VI such that U sub I and V sub I are independent random variables. We use expected value approach to formulate the problem. So the problem is to find the optimum location of the transfer point such that the maximum expected weighted distance from the facility of all demand points through the transfer point E of f of x, y is minimized. Thus, the problem is formulated as follows. As you can see there, that is the formulated for this problem. Note that E is operator of expected value. This is a general formulation such that no certain probability distribution for U sub I and V sub I, and no certain distance measure assumed. For this, this figure shows geometric representation of the above general mode. Each demand has a geographic distribution in a region, and probability of occurrence of emergency needs in each point of the region is known. Probability distribution for U sub I, V sub I may be different for different demand points. Also, each demand has its own weight. Now, we develop the model from a conceptual view and give an explanation and interpretation to justify and support application of the model. So, we define weight of demand point I, W sub I as functions of three factors. Importance of demands I sub I can be function of population number, potential of occurrence of emergency need, and other issues of demand region I. Unit of transportation cost from demand I to transfer point C sub I. Travel speed from demand I to transfer point V sub I. We consider alpha as the weight of the facilities, such as hospital, and define it as a function of three factors. A service risk, which is the risk of transportation vehicle not being available to emergency needs when they occur because the vehicle is busy. Unit of transportation cost from transfer point to the facilities, C sub C, it can be function of transportation vehicle and route specification in traveling from transfer point to the facility. Travel speed from the transfer point of the facility, V sub C, it may indicate speed of vehicles such as helicopter in traveling from transfer point to the facility. Thus, we have alpha H, R sub C, C sub C, V sub C, which is alpha is related with R sub C and C sub C directly. As the values of these factors increase, facilities' weight increase and tend to attract transfer point to reduce vehicles' travel time and cost and increase its availability. Alpha will decrease whenever VC increase to allow the transfer point to be located farther from the facility. So, patients will travel farther by means of high-speed vehicle that is desirable. We will consider the following two cases: an uniformly distributed demand in a square and uniformly distributed demand in several rectangles. Demands points to the transfer point and a Euclidean distance from the transfer point to the facility.